This is the first video in the set of videos on energy, work done and power for GCSE. Within the video, we're going to be looking at a couple of things. We're going to look at how to calculate the amount of energy in kinetic, gravitational and elastic potential stores. And we're going to make sure that we can describe changes in energy stores in different situations. And we'll have a little chat about work done as well. In the next video, we're then going to look at how we calculate work done, calculate power and calculate efficiency and use it in different situations. So let's get started. Remember, if at any point something's not making sense, just use the pause button. You can always rewind and go over something again. It might be helpful to make summary notes as you go through, or to try the practice calculations before I go through the worked examples on the video. So at GCSE, if we're going to calculate the energy in different types of stores, we have got three stores that we might have to calculate. So we've got kinetic energy, gravitational potential energy and elastic potential energy stores, and we should be able to, for any one of these types of stores, work out how much energy is in each of them. Here are the equations that we use to calculate the energy in each of these stores. For kinetic energy, we've got kinetic energy is equal to half mv squared. For gravitational potential energy stores, we've got the energy is equal to the mass of an object times acceleration due to gravity times the height. And for elastic potential energy, we've got the energy in the store is equal to half times the spring constant times the extension squared. Now remember, for the AQA syllabus, the equation to calculate the kinetic energy store is not given, so you need to remember it. The equation to calculate the amount of energy in a gravitational store is not given, so you need to remember this one. But this equation here for the energy stored in a spring, for example, in an elastic potential store will be given on the formula sheet, so you just have to remember it's there and go and look for it. A couple of quick pointers about each of these equations before we move on. Remember that if you are calculating the energy in a kinetic store, the mass has to be in kilograms, and remember it is v squared. Quite often people forget this little squared and that causes problems right at the end, which is a shame. If we're looking at calculating the gravitational store of energy, G will be given to you. It's not required that you remember that, but it's always good to remember that on Earth it's 9.8 meters per second squared. The mass needs to be in kilograms and the height needs to be in meters. And then finally, if we're calculating the elastic potential energy in a store, K is the spring constant measured in newtons per meter, and E is the extension or compression of the spring or object, and that is going to need to be in meters. Okay, so all of those points there just to bear in mind when you're using these equations. So let's have a look at a worked example. Here we go. A child of mass 45 kilograms goes down a slide 4 meters high and 8 meters long. Assuming no friction, calculate the speed of the child at the bottom of the slide. So the first thing we're going to do is draw ourselves a diagram like this and write down our knowns and our unknowns. So here I know the mass is, I've missed out 5, there's 45 kilograms, I'll put that in just a second. The height is 4 meters, and we don't know the velocity or the speed of the child at the bottom, and that's what we want to know. And I always write that with a question mark so it's easy to remember what we're trying to achieve. Here's the slide that the child is going to go down. It's 8 meters long but 4 meters high. Next thing we need to do is try and remember our equations. So have a little think, what equations do we need for this situation? So here we have our equations. We're going to use kinetic energy, the energy in the kinetic store, because we've got V here and that's what we're trying to find here. And we've got the mass, that's good. And we have got the gravitational energy is equal to the mass times acceleration due to gravity times the height. Now, one of the keys to solving this question is to remember that the energy in the gravitational store at the top of the slide is going to be equal to the energy at the kinetic store at the bottom of the slide, and that's the case because there's no friction. If there was friction, we'd find that some of the other energy had gone into heating, but we'll talk about that later in the video and in the next video as well. So the gravitational energy in the store at the top of the slide is equal to the energy in the kinetic store at the bottom of the slide. So let's carry on with that calculation. So I start off by calculating the energy in the gravitational store at the top. So I have got that the energy in the gravitational store is equal to the mass of the child, which is 45 kilograms, multiplied acceleration due to gravity, which you'll be told on Earth is 9.8 meters per second squared, multiplied by the height or the change in height of the child, which is going to be 4 meters. So if we find out what that all is equal to, we get 1,764 joules, okay? So the energy in the gravitational store at the top of the slide was equal to 1,764 joules. So what does that mean about the amount of energy in the kinetic store at the bottom of the slide? Have a little think now. And hopefully you remembered that because the energy in the gravitational store at the top is equal to the energy in the kinetic store at the bottom, that means the kinetic energy store at the bottom has also got 1,764 joules in it. Okay, so what I need to do now is rearrange this equation for the kinetic energy store to allow me to have V equals as its expression. So I've got the amount of energy in the kinetic energy store, I know the mass and I know half, so I just now need to rearrange this equation to find V. So let's rearrange it together now. We are going to say, I'm going to move the half over first. So if I've got to do the opposite of multiplying by half is dividing by half. So I'm going to say 2 multiplied by the kinetic energy store divided by the mass is going to be equal to V squared. So if I take the square root of it, that's going to be equal to V, okay? So let's just check we're happy with that. I've got rid of the half from this side over here. If I get the laser pen on, I've got rid of this half from this side by multiplying both sides by 2. So I've got 2 times the energy. That's great. I'm going to move this mass over by dividing both sides by m. So I've got 2 times the energy divided by m, and I'm going to undo this squared by square rooting. So I get V is equal to the square root of 2 multiplied by the energy divided by the mass, which is great. So the next job is to get that as an answer. So put the numbers in, find out what we get. So we're going to do the sum 2 times 1,764 divided by 45 square rooted, and that should give us 8.9 meters per second. Okay, so the speed of the child at the bottom of the slide should be 8.9 meters per second, assuming there is no friction. And obviously we know in real life there is friction, so that might be why that looks a little high. Okay, good. Let's try another one. Okay, in this situation, worked example number 2. A spring, which you can see here, is placed over a clamp stand, as shown in the diagram. The spring is compressed by 2 centimetres and then released, so it jumps up the clamp stand. The spring has a mass of 8 grams and a spring constant of 630 newtons per metre. How high does the spring jump? Let's have a little look. First of all, we're going to write down our knowns and unknowns. So I've got the extension of the spring, or the compression. Doesn't, in terms of the equation, they're both the same in this case. So I've got that as 2 centimetres. I want to know the height that the spring is going to reach. I know the spring constant K, 630 newtons per metre, and I know the mass of the spring is 8 grams. So the first thing I need to do is check that those are all in the units that I need them to be in. So have a little think, do any of these need changing? And of course the answer is yes, they do. So as we said at the beginning of the tutorial, this extension needs to be in metres. So I've converted 2 centimetres into 0.02 metres. I don't know the heights, we leave that one. This one is in newtons per metre, so that's fine. But 8 grams, our mass has to be in kilograms, so I need to convert that to 0.008 kilograms here. Next job, what equations am I going to need? Remember, you're going to be given the equation for the store of elastic potential energy in the spring, so I need to go and look that up from the formula sheet. And you need to remember the equation for the gravitational store of energy, which is the type of energy that the spring will have at the top. So here are my two types of energy. So here are our equations. We've got the gravitational potential store of energy is equal to the mass times the acceleration due to gravity times the height. And we've got the elastic potential store of energy is equal to half times the spring constant times the extension squared. So we know that the energy in the elastic store is going to be equal to the energy in the gravitational store when the spring has reached the top. So we start to put in the numbers. How much energy have we got in the elastic store when the spring is compressed at the bottom? We've got half times the spring constant, 630, times the extension squared, so or the compression in this case, 0.02 squared. And if we calculate that, we get that there is 0.126 joules of energy in the elastic potential energy store, which means we have got 0.126 joules of energy in the gravitational store when the spring is at the top, at the highest point of its jump. So we have got if we take this equation here for the energy in the gravitational store and we rearrange it to give us H, we get the energy in the gravitational store divided by the mass and the acceleration due to gravity is equal to the height of the jump. And when we put these numbers in to the equation, we get 0.126 divided by 0.008 by 9.8, and that should give us 1.607 meters. Okay, right. Now we're going to move on to the second aim of the tutorial video, which was discussing and describing energy stores. So let's remind ourselves of a couple of key points before we talk about this further. So what we want to be able to do is use changes in the energy in different stores to determine if a change to a system is possible. So for example, if you want to know whether something can fall down, you need to know whether you've got enough energy in your gravitational potential store of energy. So the energy stores tell us whether something is possible, whether a change to the system is possible. And a system is just a group of objects. So when we're looking at GCSE, we're just going to look at a group of objects in that system and see what happens. We have to remember the most important bit is that energy can be stored, it can be transferred usefully or dissipated, but it cannot be created or destroyed. So however much energy we had in that system right at the beginning, that's how much energy we're going to have in the system at the end. It might have been that some of it has been dissipated as heat energy to via heating to the surroundings, but we're still going to have the same amount of energy at the end as we did at the beginning. So if we start having a look at the stores of energy that we could have in different systems, so we're saying that we've got energy filling these stores up to different amounts, and when something happens to the system, when the system changes, it might be that energy moves from one store into another store. So we've got the three stores that we've already seen in the video that we've been calculating the value of. So we've got the kinetic store of energy, which is the store of energy something has if it's moving. The gravitational store of energy, which is the store of energy if something has been raised up and is able to fall down. We've got the elastic potential store of energy, so that's the energy that would be stored in a system if it's being compressed or extended. And then if we look at some of the other stores that we see in the GCSE course, we've got the internal store of energy of an object. It could also be known as the thermal store. So we know if an object has got a higher temperature or a lower temperature, then there are changes happening to its internal or thermal store of energy. We've also looked in the GCSE course at the nuclear topic, which is where we're looking at what changes going on in the nucleus of an atom. And we know from our study of radioactive decay, of fission, of fusion, that there is a store of energy in the nucleus of an atom. So this is what our nuclear store of energy is here. If we look at things like batteries in electrical circuits, the energy that is stored in a battery, because it's got the potential for a chemical reaction to take place, that is our chemical store of energy. It's also the type of energy it's also the energy store that we have in our muscles. So when we eat food, we have got that store of chemical energy from the food that's going to the store of chemical energy in our muscles, ready for our muscles to then do work. And then the final two stores, depending on whether you're doing GCSE or A-level or IB, and potentially what syllabus you're doing as well, they could either be known as one store or two stores. So you could have got the electrostatic store, which is the store of energy if you've got opposite or like charges attracting or repelling. And you've got the magnetic store, which is the store of energy that you've got if you're, for example, holding two magnets close to each other. But it turns out, actually, as we go a little bit further through physics, that you could refer to them as the electromagnetic store, because those two fields are connected. So those are our stores, and you'll notice actually that they link really clearly to the different topics that are covered within the physics GCSE. So you can see that this is quite a good overview topic if you're revising, to make sure you're revising the whole of the GCSE carefully and thoroughly. Now, if we review this point up here, energy cannot be created or destroyed. It can be stored in one of these stores. It can be transferred usefully, or it can be dissipated, but it cannot be created or destroyed. Now, when we are transferring it usefully or dissipating it, when we move energy from one store to another store, we are doing work. Okay, so the word work has got a very specific meaning in physics, and it is this idea that we are transferring energy from one store to another. We've got different ways that we can transfer energy from one store to another. We're going to have a quick overview of it here, and we're going to go into it in more detail in the next video, where we'll look at calculating it. If you're using this as a revision video, hopefully you'll start to see how this topic is connecting to all the other topics that you've done in the GCSE course so far. So, for example, forces transfer energy, they do work mechanically, okay? And we have got an equation that we're going to look at in the next video, saying that work is equal to the force times the distance moved in the direction of the force. So forces transfer energy from one store to another. They are doing mechanical work, okay? Another way we can do work is an electrical circuit can do work. Okay, an electrical circuit transfers energy from one store to another, and in this case the current is doing the work. Okay, and we saw in the electrical topic, in the electricity topic, equations to calculate the work done by the current, because the electrical circuit is doing work, transferring energy from one store to another. The other way that we can go about transferring energy from one store to another is by heating. We could have heating by particles, which would be sort of conduction and convection. The energy is being transferred from one thermal store to another thermal store. Or we could transfer energy via heating by radiation. So, for example, that might mean infrared radiation, that might mean the electromagnetic spectrum, that might mean nuclear decay, for example, gamma, beta, and alpha radiation. So we could also have heating by radiation. Okay, so these are the ways that we can do work, that we can transfer energy from one store to another. So the next thing that we need to be able to do is to take that understanding that we were previously discussing and use it to describe the changes in the energy stores for different situations. And we've got some of the most likely to be visited in the assessments, or most likely to come up in the GCSE course here. Whenever we're doing this, we're going to think really clearly about the start point of the system and the end point of the system, so that we can describe the changes to the stores of energy within that system. Okay, so whenever you're asked to do this, have a really clear starting point and a really clear end point in mind. So for this first one, a car is moving at constant velocity at the beginning, and at the end of that change, the car is stationary. So this involves a car decelerating. So we had a car moving at a constant velocity driving along a road, and then at the end of this situation, the car has stopped. What are the changes to the stores of energy involved for this situation? Have a little think. You might want to press pause, and then we will go through. So, how are we going to decelerate the car? We're going to need to decelerate the car by applying the brakes. The brakes are going to exert a frictional force on the wheels. Here we've got an example of mechanical work. There's a force doing the work. Friction is going to transfer the energy. Okay, what type of energy store did the car moving at constant velocity have? It was moving, so it had a kinetic store. It had energy in its kinetic store of energy. And the brakes have done work on the wheels and transferred the energy from that kinetic store into a thermal store. The brakes are going to get hot. The wheels are going to get hot. So the brakes have done work via the frictional force acting on the wheels, and the energy is transferred from the kinetic store to the thermal store of the brakes and the thermal store of the surroundings. Right, next situation. At the start, we're holding a tennis ball in your hand, and at the end of this situation that we're describing, the ball is moving through the air. So this is you accelerating an object, okay? We're accelerating this object with a constant force. We're holding a tennis ball in our hand, we accelerate the tennis ball, we let go of it, and it's flying through the air. So what are the changes in the energy stores involved in this situation? Press the pause button, have a little think, and then move on to the answers. So let's start off by thinking, how is the work being done in this system? If we've got a transfer of energy from one store to another, what is doing the work in that system? And in this system, we have got our hand exerting a force on the ball as it's accelerated, okay? So we're holding the tennis ball, we do work on that tennis ball, we transfer energy from one store to another, and then we accelerate the ball and it's moving through the air. So the hand exerts a force on the ball as it is accelerated. The hand does work on the ball, transferring energy from where was the energy to start with? If we are accelerating the ball, the store of energy at the beginning was the chemical energy in our muscles, and the energy has been moved from that store into, if this ball is moving, the kinetic store of the ball. So the hand does work on the ball, transferring energy from the chemical store in the muscles to the kinetic store of the ball. Okay, hopefully this is making sense and it's going well. Let's try another one. We have got an object moving towards an obstacle. It's not looking positive. And then at the end of this situation, the object hits the obstacle and stops moving. Hopefully no one got hurt. So let's have a little think. Maybe press the pause button. Have a think. What are the changes going on in the stores of energy in this system? So let's think about the start and the beginning. At the start, the object was moving. So that makes us think there was energy in a kinetic store. At the end, the object isn't moving. So the energy has come out of that kinetic store. So something's been doing work transferring energy. So the kinetic store of the object has been transferred to the internal store of the object, or thermal would be acceptable as well, of the object, and the obstacle. So the object involved in the collision has increased its internal energy, and the obstacle that was collided into has increased its internal energy as well. Final one for luck. Cold water in a kettle. At the end of the situation, we have got hot water in a kettle. We can assume that we switched the kettle on in the middle of this. Press the pause button, have a little think. What changes are happening to the stores of energy in this system? So, we've got a heater in the kettle, okay? The heater in the kettle is transferring energy to the internal store of the water by heating. Okay, so this energy is being transferred, the work is being done by heating. If you want to take this a little bit further, you can say, well, where has the heater got the energy from that it transfers into the thermal store or the internal store of the water? And that energy is being transferred from the national grid to the heater by the current. Okay, so we've got current doing work, transferring energy from the national grid to the heater, and then work is being done via heating to transfer the energy from the thermal store of the heater to the thermal store of the water, so that we get hot water in the end. Let's see now if we can apply this understanding of how the stores of energy change in a system as it changes to the two questions that we looked at before, a child going down the slide and a spring popping up. Okay, so let's have a little think. Press the pause button. Can you describe the changes in the energy stores for these two systems? So let's start with the child. At the beginning, the child is at the top of the slide. At the end, the child is at the bottom of the slide. Energy is being transferred from one store to another. How is it being transferred? It's being transferred by a force. There is a force doing mechanical work on the child. That force is gravity. Gravity does work on the child, transferring energy from the gravitational store that it had at the top of the slide to the kinetic store that it has at the bottom of the slide. Now, in the question that we did to start with, we assumed there was no friction, which we can do in physics land. In real life, not quite the case. So if you wanted to take it a step further, because let's say we had to describe the impact of the role of friction on that slide as well, we would say that the force of friction is going to do mechanical work as well. It's going to transfer energy from the kinetic store of the child, to the internal or thermal store. So that would be of the slide and of the child's clothing. Both of those, the internal store is going to increase via heating, because the force of friction is always going to end up transferring energy to the thermal stores. Okay, that's what friction does. Having a little think now about the spring popping up. So when the spring is compressed down, there's energy in the elastic store. We release the spring rises, and the energy in the elastic store is transferred into the kinetic store. If you wanted to take it a bit further until the spring gets up to its highest point, the energy from the kinetic store is transferred into the gravitational store. So when the spring is at its highest point along that clamp stand, all of the energy that was in the kinetic store has been transferred into the gravitational store. So hopefully that has all made sense. If you've got any questions, bring them to the next lesson. The two things that we were aiming to do in this video, we were aiming to calculate energy in the kinetic, elastic and gravitational stores, which we've practiced. You might want to do some more practice questions now, just to really consolidate that skill. And we wanted to make sure that we could describe energy transfers from different stores in a range of different situations, and we've looked at quite a few different examples there. In the next video, we are going to be taking this idea of work done a bit further. So rather than just describing the 4 different ways of doing work, we are going to review what we've done so far in the Physics GCSE course and practice calculating the work done for different situations. So we're going to look at how we calculate the work done mechanically by a force. We're going to look at how we calculate the work done by a current in an electrical circuit, and we will look at how we calculate the work done via heating, looking at specific heat capacity and latent heat. We will then also look at how we calculate the power and how we calculate the efficiency and ways to improve efficiency in different systems. I hope you found that useful. Remember to check out the next video, bring summary notes and questions to the next lesson. Well done.